Hello, this is Javid. In this video, I'm going to be talking about internal stability of continuous time systems. This video presumes that you've watched and understood the videos on bounded input, bounded output stability of continuous time systems, and it also assumes you understand the time domain solutions of continuous time systems. Those two things come together in this video. So we're going to be talking about systems that have a zero input response. In the bounded input, bounded output stability video, we considered zero state response, and we know in general that the general response of a system is the sum of the zero input response and the zero state response. So when we say zero input response, what we mean is we're talking about something where u is just by definition zero. And so really what we're restricting ourselves to in this discussion for right now is a simple linear system that looks like x dot of t equals a x of t, and we are still considering LTI systems where a is not a function of time. And we know that the solution of this equation looks like e to the a t times x naught, where x is the initial condition. So that's why we call this the zero input response, as opposed to the zero state response, which is what we considered in the last video. So now the assumption here is that the state x naught is not zero, that there's some number here. Otherwise, e to the a t times the zero vector is just a zero, and that's just a trivial solution where x just sits at zero for all time, which is very interesting to us. So as we're looking at the stability of this system, we have to define a couple of types of stability that we're going to talk about. So the first type of stability is known as Lyapunov stability. And sometimes people say stability in the sense of Lyapunov. So basically, stability the way that this Russian guy Lyapunov defined it. So let's call that Lyapunov stability for now. And what Lyapunov stability says is a system is Lyapunov stable if every finite x naught, so every finite initial state excites a bounded response. And when we say finite x0, what we mean is that those are real numbers. If the initial state is infinity, we shouldn't be surprised if the state at some point in time goes to infinity because it happens right at time zero. So we want to say that our initial state is some real number, and then that is going to excite a bounded response, meaning that x of t over time, if I were to plot x of t over time, I can always find some number that no matter how crazy my signal gets, I can ensure that it doesn't ever go outside of those bounds. So this is a really kind of simple sense of stability. It just means your signal doesn't grow to infinity. And this is the way that Lyapunov defined this kind of stability. Now, sometimes people also use the term marginal stability to describe this type of stability, but that's a term that tends to stick to sort of textbooks, and it's not the way people use the word marginal stability in practice. So in a moment here, I'm going to define a sort of a different version of marginal stability, which is more in line with how people use it, and that's the way we use it in this class. So for this class, this concept here is called stability in the sense of Lyapunov, or Lyapunov stability. The next type of stability that we're going to look at is known as asymptotic stability. And so what asymptotic stability is, let me write that. Asymptotic stability. And a system is asymptotically stable if every finite initial condition excites a bounded response, and I should say that approaches zero as time goes to infinity. So basically, x of t goes to zero as time goes to infinity. So this is a type of stability that has this sense that not only do things not go to infinity, but they actually decay away to zero over time. And if you look at the definition of Lyapunov stability, every finite initial state excites a bounded response, and asymptotic stability, every finite x naught excites a bounded response, that goes to zero as time goes to infinity. You see that if a system is asymptotically stable, it's also Lyapunov stable. But you can easily imagine Lyapunov stable systems that are not asymptotically stable. So in this class, when we say a system is marginally stable, what we're going to mean is that a system is Lyapunov stable, but not asymptotically stable. So this is the definition of marginal stability we're going to have. So we're basically saying every finite state excites a bounded response, and that bounded response does not decay away to zero. That's what we're going to describe as a marginally stable system. So, when you're picturing something that's marginally stable, you should be imagining in your mind is something that has a response that I started at some initial state, and then it sort of oscillates forever and never decays away. These are the types of systems we're going to call marginally stable. They're bounded, so they're clearly Lyapunov stable, but they don't decay away to zero over time, so they're not asymptotically stable. So these are the three definitions that we're going to use in this class. And what we want to do now is we want to talk about how the eigenvalues of the A matrix relate to these concepts. So we say that this equation, x dot of t equals a x of t, is asymptotically stable if and only if, so this is this two-way arrow, if and only if all eigenvalues of A have negative real parts. So we're saying if the system is asymptotically stable, then it has all its eigenvalues of negative real parts, and we're saying if A has all its eigenvalues of negative real parts, then it's asymptotically stable. And again, if we look at the real imaginary plane, the complex plane of our eigenvalues, it's okay if they're here, it's okay if they have complex components, as long as the real part is negative. And so this again is referring to the open left half plane. So we're not including the imaginary axis, because that wouldn't have a negative real part, it would have a zero real part. So this is the definition of a system being asymptotically stable. And the reason why we have that, we've looked at the solution to this equation. If we know the solution to this equation looks like e to the at times x0, and we know that we can always, if A is not already a Jordan form matrix, we can always, through a similarity transformation, convert it into a Jordan form matrix. We know what e to the at looks like if it's a Jordan form, and we know that we tend to have things that look like this in our Jordan form. And as long as that's a negative number right there, then we tend to have things that over time look like decaying exponentials, which is the exact flavor that we imagine in our mind when we think about asymptotic stability. Now, what does it mean to be marginally stable? So we say that this equation, x dot of t equals a x of t, is marginally stable if and only if, so this is two-way arrow, so all eigenvalues of A have zero or negative real parts, and those with zero real parts are simple roots of the minimal polynomial. of A. So what does this mean to us in some language that we can actually try and remember? What it means is when we look at the Jordan form of our matrix, let's just draw sort of a Jordan form here. Our Jordan form is going to consist of blocks on the diagonal. And we want these blocks to have negative numbers or zeros. But if they're zeros, we want them to be in Jordan blocks of order 1. That's what this means. So this matrix here, if I say, let's say I have a Jordan block, I have 2 eigenvalues at negative 2 in a Jordan block, and then I have an eigenvalue at 0, and I have an eigenvalue at -1, and I have an eigenvalue at -1, 1, -1. So these are my Jordan blocks. This system is marginally stable. Let's look at that. All the eigenvalues of A have 0 or negative real parts. That's true. I have -2, -2, 0, -1, -1, and -1. And those with 0 real parts, like this one here, are simple roots of the minimal polynomial. What that means is it only exists in a Jordan block of order 1. This system here is marginally stable. Let's now consider an example that's not marginally stable. So let's say, up until this point it looks the same. That Jordan block's the same, that Jordan block's the same, that Jordan block's the same. And now this Jordan block changes like this. So now my eigenvalues are 0, 0, 0, -1, -1, -1. But I have 0 appearing in a Jordan block that's more than order 1. That Jordan block right there means this is not marginally stable. And if we have a system that is not marginally stable and also not asymptotically stable, then it is unstable. So this is an unstable system. And why is that? Why is this okay, but this is not okay in terms of stability? We have to go back to our time response. If our time response of our Jordan block, let's consider a Jordan block that really does look just like a 0. We saw that e to the jt of this looks like e to the 0t, which looks like e to the 1, which is just a constant, e. So if I plot this over time, here's time, here's e, I get a nice bounded response. It's not growing to infinity, it's also not decaying away, so it's marginally stable. One eigenvalue of 0 is not bad to us. The initial condition just stays. It doesn't decay away, but it doesn't grow to infinity. But if we had a Jordan block, if we had a Jordan block that looked like this, if you remember what the time response looks like, the time response for the first state looked something like this. It looked like e to the 0t plus t e to the 0t. So now this thing looks like e to the 1 plus t e to the, or excuse me, this is a mistake here. This isn't e to the 1, this is just 1. Sorry about that. That's my bad. So now I have e to the 0 is a 1. Anything to the 0 power is a 1 plus t e to the 0, which is again, so I'll rewrite this. It looks like 1 plus t. Now this does not. Here's time. Here's 1 plus t. It looks like this. And it's growing to infinity. So when we have Jordan blocks of more than order 1, we get things like this happen. And if we have a Jordan block of order 2, it looks like this. If it's order 3, we get a term that looks like this. And all of these terms grow to infinity. And so it's only this first term that doesn't grow to infinity on. So that's why it's okay to have a 0 eigenvalue, provided it's in a Jordan block of order 1. We can't have any of these happen. And the Jordan blocks of other eigenvalues of higher order don't matter to us again, because if we have something that looks like this, then we have something that looks like x of t equals e to the minus t plus t e to the minus t. And if you remember what this term looks like, it looks something like this. And d squared e to the minus t looks something like that. And d cubed e to the minus t looks something like that. So while they may grow for a while, eventually the e to the minus t dominates the t to the n power and decays away to 0. So it's okay to have Jordan blocks of higher order for all the other negative real part eigenvalues, just not for the zeros. So the last thing I want to say about this simple equation that's on force is that the internal stability of a system isn't changed by an equivalence transformation. So if we have some system, if we change our system to some new a bar system, like this, where Q is some transformation matrix, that a bar has all the exact same eigenvalues as this a. So all of these notions of internal stability that you define, since they're based on the eigenvalues, they fundamentally don't change. So now we've only been considering the system x dot of t equals ax, and that's a very important equation for us. But let's now try and tie this back to this notion of a bigger system, where we have something like this, and we have y of t equals cx of t plus du of t. So we remember we can create a transfer function for this system, where I have my output as a function of my input. And I probably actually shouldn't write it this way because these are vector notions, so I can't do it divided by. So let's write it like this: that y of s is equal to c times si minus a inverse times d plus d times u of s. And we call this whole thing our transfer function matrix for a multi-input, multi-output system. We call that matrix g of s. So this is the system we considered when we were considering bounded input, bounded output stability. So let's see how internal stability relates to this idea of bounded input, bounded output stability. So one thing we find that as we look at the mathematics of this, we find that every pole of g of s is an eigenvalue of a. So every pole of g of s is an eigenvalue of matrix A. If my system is asymptotically stable, then I know that it's also bounded input, bounded output stable. But I can't say the same in reverse. So even if my system is bounded input, bounded output stable, it does not imply that it is asymptotically stable. Now this is not the same as not equal, it's the same as doesn't imply. So if my system is asymptotically stable, it does imply it's bounded input, bounded output stable. If I already know this is true, then I by default know this is true. But even if I know my system is bounded input, bounded output stable, I don't know for a fact that it's asymptotically stable. It might be, I just can't presume that. So let's recall the total solution of this equation, where x of t looks like e to the at x naught plus the integral from 0 to time of e to the a evaluated at t minus tau times b times u at tau d tau. So this was the total solution of our equation. So if we have an equation like this, when you look at this thing, when we dealt with bounded input, bounded output stability, we were talking about the 0 state response. So it presumed that this was 0 here. So that's how bounded input, bounded output stability was defined for this being 0. We could make, but what that basically means is if this thing is 0, then a bounded input leads to a bounded output. The problem is that it's very rare and difficult that your initial condition would be exactly 0. Even a tiny little difference from 0, a tiny little bit of noise, a tiny little position error in your system will make your initial state non-zero. And if it's non-zero, then who cares if it was only bounded input, bounded output stable? Because if there's any instability that happens here, you're going to see it from that non-zero initial state. So even if you think your initial state is 0, you have to sort of presume that it's not exactly 0, it's some number away from that. So when what do we know just to conclude this this talk on internal stability? We know if our system has stable eigenvalues, I'm going to use the term stable eigenvalues. So when I say a stable eigenvalue of A, what I really mean is that it has a negative real part. So it's this term stable, it's sort of in the asymptotically stable way. So if your system has stable eigenvalues, then we know it has stable poles, and stable poles is defined in the same way with negative real parts. And if it has stable poles, then we know it's not stable. What else do we know? If we have stable eigenvalues, it also means the effect, this is based on this here, the effect of our initial condition, x naught, on x of t goes to 0 as time goes to infinity. So what that means is, yes, our initial state where we start from, it doesn't matter. I mean, this initial state does appear here, but after some amount of time, the contribution of that goes away to 0 if we have a stable system. And so eventually, you can't tell where you started anymore.